Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're still in the realm of thermodynamics, and we're looking at a heat pump problem, one that I particularly like. This is problem 600, and it reads like so. A Carnot heat pump is to be used to heat a house and maintain it at 25 degrees Celsius in winter. On a day when the average outdoor temperature remains at 2 degrees Celsius, the house is estimated to lose heat at a rate of 55,000 kilojoules per hour. If the heat pump consumes 4.8 kilowatts of power while operating, determine A. How long the heat pump can run on a day. B. The total heating costs, assuming an average price of 11 cents per kilowatt hour of electricity. And C. The heating cost for the same day if resistance heating is used instead of a heat pump. So let's start by doing a little drawing. I'm going to draw a house with my beautiful drawing skills. Probably do one of these houses. All right. So what we have here is a house in a day that is 2 degrees outside Celsius, and the house is 25 degrees Celsius inside. And obviously, because there's a difference in temperature between the outside and the inside, there will be a heat transfer occurring. And this heat transfer, we happen to know, is exactly 55,000 kilojoules per hour. Okay, so let's read the problem again and do some analysis. First off, a Carnot heat pump. This is super important. Why is that? Because a Carnot heat pump, right? When they say that there's a Carnot heat pump, what they're implying here is that this is a super efficient heat pump, or I should say, this is the best possible heat pump in terms of irreversibilities, or in other words, the best possible heat pump in terms of the second law of thermodynamics. There's no entropy generated when using this Carnot heat pump, right? Every single process through which this pump goes is completely reversible. And you'll see why that's important further down the track. We are from 25 to Celsius. We are with a funny unit of kilojoules per hour, which we're going to obviously convert to kilowatts so that we can use better units. We have the heat pump that requires, this is the amount of energy we need to put into the heat pump for it to work. And we want to find out how long it can operate in a day. So for A, we want a unit of time, right? How long? Some unit of time. For B, the cost. So we want to find out what does it cost. And C as well, the cost, but then in a different scenario. Okay, so to be able to find out how long it should operate for, we need to find out, how much energy is being lost. If what we want to do is keep the situation as is, right, not change anything, then we need the heat pump to provide this house with exactly the same amount of energy, right? If the heat pump is providing this amount of energy, then nothing's going to change inside the house. It's going to lose some, gain some, exactly the same amount. So it's going to stay at 25. Outside is going to stay at 2, right? Beautiful. So what we need to do is find out how long this heat pump operates for. How efficient is this heat pump? What's the capacity of this guy to providing heat back to my house? Well, to find that out, we use something called the coefficient of performance, COP, right? And the COP is defined as the desired output, what I desire in the output of it, divided by the required input, right? And I would love for you guys to, not sure memorize is the best word, probably learn COP as this, right? Just like we learned about efficiency, the what I gain for what I give, the COP can be understood this way. And then regardless of what scenario you have, you can always deduce the COP by yourself. Okay. So if this is the case, let's think about now, let's do a quick diagram of the situation we have. We have a cold reservoir and a hot reservoir. Cold, see. We have our heat pump here, heat pump here in the middle. And what would happen, right, if we didn't have any heat pump here is that we would have energy traveling from the hot reservoir into the cold reservoir, right? Simple heat transfer. However, the idea of having a heat pump is precisely to, reverse that, right? So what we want to do is send energy this way, right? So we want to send energy from a place that has lower temperature into a place that has higher temperature. But to do that, we know we need to give this heat pump some energy, right? Because this is not what entropy would dictate. So we need to put some energy in. All right. This is the situation we have in our house. So given this situation and given, this idea of what the COP is, what we now do is, okay, what is my desired output? Well, what I'm looking for is to heat up my house, to be able to send energy into my home, right? Into the place that is already hot. Remember that our home is at 25, outside is 2. What I'm trying to maximize, that my desired output is to maximize the amount of energy going into the hot reservoir. So my desired output is my COP. My desired output is to maximize this guy here, right? What I called QH for hot. And my required input is whatever energy I need to give for that to happen. And the energy I need to give is this guy here, right? So know that, we know this is 4.8 or something, right? But we don't know yet this amount of energy just here, right? We can calculate what will be the required COP for a given a generic heat pump. But in our case, we want to know exactly what is the COP for our heat pump, which is a Carnot heat pump, right? And because of that, what we can do is, let's do some math here. First, let's apply the first law of thermodynamics to this simple system here. So let's take this guy as our control volume, and we're going to note that if energy cannot be created or destroyed, that means that the energy in, or power in, are these two, and these guys, and this guy here is the output. So this is true because of the first law. I'm going to substitute, then here we're going to have on the bottom there, I'm going to substitute this by this minus this, right, which is the same thing. So QH minus QL. And then what I can do here to simplify my life is I'm going to divide both top and bottom by the same thing, which is the same thing as dividing by 1, right? And this is going to give me 1 on the top there. And then here in the bottom, I'm going to have 1 minus QL divided by QH. Right, and I'm going to use this form here. Why? Because, note the following. Because and only because this guy is a Carnot heat pump, that's why it's important to know it's a Carnot heat pump, I can make a transformation here. All right, I'm capable of making a transformation here and going from this equation here into one very similar, yet without the Q's and with the temperatures of the reservoir. So I'm going to remove this guy here. This is going to be my cold reservoir. This is going to be my hot reservoir. Okay, why is that important? Well, first off, we know what is the cold reservoir and the hot reservoir. We've known that all along, right? Second off, this is possible because this is a Carnot heat pump, and a Carnot heat pump does not have any entropy being generated, right? So if that's the case, and because that's the case, then I can calculate what is the coefficient of performance of this idealized, I should say, heat pump, right? And then I can calculate this. So going back to the idea, okay, I'm going to calculate what COP, which will just be 1 over 1 minus, what is TC? It is 2 plus 273, because don't forget, this has to be in Kelvin. Students love to forget this has to be in Kelvin. And there on the bottom there is 24, was it? I forget. Oh, was it? 25 plus 0.273. So this heat pump here, it has a coefficient of performance of 12.95. And this is great, right? Because this means that for every dollar I put here, I get $12 up here. Kind of this, right? For every kilowatt of energy that I put here, I'm getting 12 kilowatt of energy out. And that's why it's so efficient or so good to use something like a heat pump, right? So this is the coefficient of performance of my Carnot heat pump. And this now means that if I need if I'm operating with this guy here and I know how much it consumes, I can calculate how long it needs to operate in a day to be able to provide all the energy that is required, right? So remember that we know the amount of energy being lost. This is the amount of energy being lost here. And we can convert that. I'm going to go ahead and convert that now. We have 55,000 kilojoules per hour. And we know we have 24 hours in one day, right? So this means that I have 1.32 times 10 to the 6th kilojoules per day. That's the amount of energy I lose in one day. Okay, and I know how much where's my heat pump needs to work now, right? Because my heat pump is going to work according to this. I need to supply, let's invert this. I'm going to say how much energy I need to supply. This is just going to be QH divided by COP, right? So how much energy I need to supply. This is just going to be, I need to remove 1.32 times 10 to the 6th kilojoules per day. And my coefficient of performance happens to be 12.95. No units there, right? So this means that the amount of energy I need to supply WN, work in, is 101.88 times 10 to the 3rd kilojoules per day. Okay? Or, right, if we were to simplify this, it's just 12 times less the amount of energy that I need to remove from my house. Okay, so this is the amount of energy I require, and I know my pump can provide 4.8 kilowatts. Right, so now note that we have the following. We know the amount of energy. This is energy. I should have removed this dot, because this is energy. I know the amount of energy required that my heat pump needs to remove from my house. Energy. And I know the power of my pump, of my heat pump. And the question is, what is the time that this needs to operate? Well, that's super easy, right? Because I know that power is simply the rate at which energy changes with time. So if I'm looking for time, well, that's super easy. If I'm looking for time, all I need to do is take energy and divide by the power. Right? So in this case here, the energy required is 101.88 times 10 to the 3rd, and that will be kilojoules per day. And I have a heat pump that operates with 4.8, consumes 4.8 kilowatts. 4.8. And remembering that kilowatts is the same thing as kilojoules per seconds, right? So kilojoules per seconds. So what does that mean unit-wise? We get rid of this, and we're going to have a unit of seconds per day, the amount of seconds it needs to operate per day. And this gives me, number-wise, I get that this is 2.122 times 10 to the 4th, and this is seconds per day. Weird unit, right? Weird number, weird unit. I don't want to know how many seconds per day this operates. I'd rather have how many hours per day. Well, easy, right? If I know it operates 2.122 times 10 to the 4 seconds per day, and I happen to know that 1 hour has 3,600 seconds, then I can remove the seconds and I'll be left with 5.895 hours per day, which happens to be exactly what we were looking for. Right? So this heat pump, to keep my house at 25 degrees Celsius in a winter day in which the outside is at 2 degrees Celsius, needs to operate only for about a quarter of the day, right? About 6 hours out of the 24 hours of the day.